Okay, this is Student Notes 11.4, Tangents and their Properties. Okay, the first thing we're going to do is start out with a theorem. Draw ray PQ extending past Q, then stretch a tangent to the circle at point Q on the circle. Okay, first thing we're going to do is stretch a ray from P through Q. Okay. So this is a ray, so it has an arrow on one side of it. And then sketch a tangent to the circle at point Q. So our tangent line, remember, just touches this circle at one point, and that one point is at Q. So I'm going to do the best I can to draw a line through Q. It's not the best line, but you get the idea. So if we have this situation happen, then we can come over here to the theorem. If a line is tangent to the circle, then it is perpendicular, so there's that symbol for perpendicular, to the radius. Okay, so that's what we have right here. This tangent line is perpendicular to the radius. And if a line is perpendicular to the radius of a circle at a point on the circle, then the line is tangent to the circle. Okay, so basically what we have here is that if you have a radius and a tangent line and they meet at one point, then they are perpendicular, they make a right angle. So if we look at example 1, we have a tangent right here, and we have a radius PQ. So from what we just learned, we can say that that angle is a right angle. So if we know that this is a right angle, then we need to find PQ, which is this length here. We don't know what the radius is. But as you can see right here, we do have a right triangle. So we would use Pythagorean theorem to figure out what the radius is. Okay, so I'm going to say x is our A. We don't know what that is. Plus B has to be 12. And C would be our hypotenuse here is 13. This is a triple. I already know what it is. I don't even have to use Pythagorean theorem to know. But let's say you didn't know. You could use Pythagorean theorem. So 12 squared is 144. 13 squared is 169. Subtract 144 from both sides. And x squared is 25. Obviously, when you square root the x squared, the square root of 25 is 5. So PQ, which is our radius, is 5. Okay, we're going to save example 2 for class. Example 3 is another theorem which says if two segments are tangent, two of them, to a circle from the same external point, then, okay, well, let's make an external point here. There's our external point. We're going to make two lines that are tangent. They go through this point, and they're also tangent to the circle. Nope, that wasn't a good one. Let's undo that. Okay, it's close enough. Then both of these segments right here are congruent. And the segments are congruent. So if this was 20 in length, then this would have to be 20 as well. Okay, nice and easy. So let's look at example 3. Again, we have two lines that are tangent. They go through the same external point. So we have 3x plus 2 on one of the segments and x plus 8 on the other. And we know that they are congruent to each other. So in order to find x, we would need to set them equal to each other. Take the baby to the mama. and we subtract x from both sides. So 2x plus 2 is equal to 8. Then subtract 2 from both sides. So 2x equals 6. And our last step would be to divide 2 from both sides. So 6 divided by 2, x is 3. Okay, we're going to save example 4 for class tomorrow. Go ahead and turn on the back. We're also going to save these 2 boxes up here and example 5 for class. So we're going to come down and look at the common tangents, these 2 boxes right here. Okay, the common external tangent theorem talks about tangents that are external to the circles. One looks like this, and the other one like this. So they are outside of our 2 circles. They don't cross in between the 2 circles. So we're going to label these 2 tangents as L and M. So line L and line M are common external tangents. These are common external tangents. Common internal tangents means that the 2 tangents cross each other in between the 2 circles. Let me see if I can get this to look right. There we go. There's one, and there's the other. So they cross in between the 2 circles. So these are common internal tangents. This would be like P, and this one would be Q. So these are common internal tangents. Okay, so we're going to look at example 6. Find Y. This should look like a familiar problem because you've seen a problem like this before in the past when we did our proportions or similarity unit. And what we know is we have a triangle inside of another triangle. So here's a small triangle, and then the larger triangle So what we know about these 2 triangles is that they are similar. So we need to set up a proportion to find y. So let's talk about our small triangle first. We have like a base and a height right here. So we could say 5 over 12 is equal to, okay, what corresponds with 5? The 10. 10 over 12 is the height of the small triangle, but the height of the large triangle is this whole section here. So we would need to say y plus 12. Not just y, it would be y plus 12, the whole thing. So then in order to solve for y, you would just cross multiply. 12 times 10 is 120. And cross multiply this side. We need to distribute 5 times y plus 12. So 5 times y is 5y, and 5 times 12 is 60. And then we would just simply need to work backwards to solve for y. Subtract 60 from both sides. So 120, 60 is equal to 5y, and then divide by 5. So y is equal to 12. Okay, we're going to save example 7 for class tomorrow, and I will see you guys then.